So we were talking about coarse graining dynamical systems such as maps, and we saw how in the case of a simple tent map, an asymmetric tent map, we saw that the coarse graining into two cells, a left cell and a right cell, led to a matrix W of transition probabilities, and I left it to you as an exercise to check that this really was the transition matrix for a Markov chain. So I hope you have done it and convinced yourselves that indeed the dynamics reduces to that of a Markov chain. Let me spend a few minutes now and explain a little more in detail what we mean by a Markov chain, so that in general this concept becomes familiar to you because it is extremely useful. This is the discrete time analog of a continuous time process, a Markov process, which we talked about a little bit. So let me explain again what we mean by Markov chains. Okay. So we imagine there is a random variable which takes on a discrete set of values. Suppose you take these values to be x1, x2, x3, etc., and we work in discrete time, just as in the case of maps. And let me label the values of these of this random variable x sub j, j equal to 1, 2, 3 and so on. So I label these values by just j, and when the random variable takes the value xj, I say that the system is in the state j. So from now on we do not worry about the x's itself, we just talk about the state of the system, and that is labeled by an integer. This set of integers could be finite or infinite. So the number of possible states of the system could be finite, could be infinite, but it is discrete and countable in this fashion. And now we ask, what is the probability p that at some specific instant of time n, discrete time, the state is j. That is the probability that the system is in the state j at the time n, and we ask what is the sort of rate equation you write for this, and this becomes on the right hand side, because we have now a discrete set of states, you have a summation rather than an integration, and this probability depends on the preceding step and nothing more than that. So it is equal to p, a summation over all the possibilities k, pk of the probability that the system is in the state k, and then makes a transition from the state k to the state j at a certain rate, a transition rate which we wrote as w. So this is equal to w from the state k to the state j. So w, I am not sure how I wrote this the last time. We wrote this as w j k. I wrote this as w j k or k j, it is a matter of k j.
From a state j to a state k is k j.
Yeah, this is the initial state and that is the final state. So what did I write this as?
jk.
Jk. Oh, I just wrote it in the same order. Jk. Transition probability from state k to state j. That was my definition. So this becomes w wj k pk at time n minus 1. Having reached the state k at time n minus 1, it then jumps from k to j, so that it contributes to pj of n at time n, minus there is a loss rate which is kj pj at time n minus 1. This is the chain equation. This in fact is the master equation, not the chain equation, it is the master equation for a Markov chain. Okay. Now of course you have to specify some initial condition, you have to say in what state the system is in, could be in a distribution of states or could be in a specific state. If it is in a given state, then of course you would say pj at time 0 if this thing here is in a specific state, let us call that state L for instance at time 0, then this thing becomes equal to delta J L. Okay. So it is 1 if J is L and 0 otherwise. So the task is to solve this this equation here with those initial conditions, and of course exactly what we wrote down earlier comes through, and that is if I define a vector, a column vector P of n which consists of P1 of n, P2 of n, etc., then this whole business could be written as Pj of n is W times P of n is Wp at n minus 1, where there is a certain matrix whose elements are given, can be read off from this equation, and this of course immediately implies that P of n is equal to W to the power n P of 0, and that is the formal solution to the Markov chain. Now there is a way of classifying these Markov chains. This is a systematic classification depending on what kind of transition matrix or matrix of transition probabilities W that you have. Okay. If it is possible to go to any state in the Markov chain from any initial state, then we say that this chain is irreducible, because there is a connection between any state and any other state, maybe not in one step but given enough time. If this is true, then this chain is irreducible. If it turns out that there is a flip flop between a few states, for instance if from state 3 you go to 5 to 7 and back to 3 and so on, then you can have these periodic cycles, these Markov chains in between. But if no such periodic cycles exist, then you say the chain is aperiodic, and in general the non-trivial cases are those where it is non-aperiodic as well as irreducible, so that all states are connected up in this fashion. So everything depends on the nth power of this matrix, and we know that this matrix can be put in Jordan canonical form by a similarity transformation, after which raising it to the nth power is a matter of algebra. So in principle this Markov chains can be solved. Some technical difficulties arise if this summation goes on till infinity. So from 1, if it goes up to infinity, then you have to worry about convergence. Some questions of convergence of these matrices, of what you mean by the nth power for arbitrarily large n and so on arise. Some technicalities arise, but otherwise in principle this is all that a Markov chain does. Okay. And the whole thing is guided by what this W does. This thing here. A very important question, which is important for us too in the context of dynamical systems, is does this thing reach a steady state at all? Is there any stationary distribution associated with it? Is there a quote unquote analog of an equilibrium state, an analog of critical points in the case of dynamical systems, or fixed points in the case of maps? Is there an analog of that in Markov chains? And the answer is yes, and that is very important. We would like to know if after a long time if there is any invariant probability distribution, just like an invariant measure. Is there something that does not change under further time iteration at all? So is there a limiting form to this as n tends to infinity? Is there some kind of equilibrium distribution? If so, it says that the distribution at time n does not change at all from that at n minus 1 as n tends to infinity, and that would happen when you equate this to that and you solve for the invariant distribution on both sides. Okay. If you recall, in the case of continuous time Markov processes, in continuous time we ended up with an equation which looked like delta p over delta t was equal to some W on P of t, and I pointed out that the stationary distribution would correspond to a right eigenvector of W with 0 as the eigenvalue, because you want delta p over delta t to be 0. So you would like to have a non-trivial eigenvector such that when W acts on it from the left you get 0 on the right hand side, and the right hand side was pretty much something like this, except that it was in continuous time. And what did we say then? Well, if this vanished, if this quantity vanishes, then you have a steady distribution. There are many ways in which this sum can vanish. You would have to solve a set of homogeneous simultaneous equations, but one important way which happens in many physical problems is if each term in this bracket vanishes, if term by term this vanishes, then you have a steady distribution which obeys a principle called detailed balance. In other words, if the steady or equilibrium distribution, let me label it as P equilibrium J, it is independent of time, this thing here, one possible solution is that this solution is such that Wjk P k equilibrium is equal to Wkj equilibrium, and this is called detailed balance. It is the detailed balance condition which is sufficient to produce for you an equilibrium solution, because it just says that the equilibrium distribution is just the ratio of these rates, Wjk over Wkj gives the ratio of Pj equilibrium over Pk equilibrium. And of course you could ask, but that only gives a ratio of these probabilities, how do I find the numbers themselves? What would you say? I would normalize, the whole thing has to be normalized to unity, and that gives the overall constant. So this is a very, very important subclass of possibilities. This is an important class of possibilities where you have detailed balance, and of course whether it obtains or not depends on the physics of the situation. Okay. I mention this because we will come back to this, we will see that there are reactive diffusive equations where we are going to impose the detailed balance conditions based on physical considerations. Yeah. Yeah. If it has a non-trivial equilibrium distribution, yes, certainly. Yeah, if it is an aperiodic irreducible chain, then and it has an equilibrium distribution, it will certainly be ergodic. Yes, it will jump from one to the other. It is not saying that things are going to stop, it is just like an invariant measure. So the dynamics continues, it is just that under time evolution that distribution does not change, right. So for example, the gas particles in this room, if I assume that these collisions have sufficiently short term memory that the processes are all describable by Markov processes, then look at the velocity distribution of the particles of gas in this room. It is a Maxwellian distribution under equilibrium conditions. And the whole idea is, in spite of the collisions going on, in spite of the dynamics going on, the Maxwellian distribution does not change. So it is an invariant distribution, it is an equilibrium distribution. So that is exactly the point. It is exactly like saying, we went back a few steps, saying that the density, phase space density obeys an equation like H with rho, and the whole point of equilibrium statistical mechanics was that in equilibrium, thermal equilibrium, this is 0. So we discovered that those distributions, the phase space distributions, had to be functions of the Hamiltonian. What functions they were depended on the external conditions. If you kept a system in isolation, a closed system in thermal equilibrium, then that density is uniform on the energy hypersurface, that is the microcanonical ensemble. If you kept it in contact with a heat path such that it could exchange energy with the surroundings but not matter, but not mass, then this rho was some specific thing called the Gibbs distribution. It was e to the minus beta h, where beta is 1 over kT, Boltzmann's constant times the temperature. If you kept it as an open system which could exchange matter as well as energy with the surroundings, then you worked in the grand canonical ensemble, and this rho involved not just the Hamiltonian e to the minus beta h, but there was an extra factor which depended on the chemical potential of the system and the number of particles in it. So this thing here is just, this is precisely, this is an example of the kind of invariant distribution that you deal with in physical situations. The point I am making is that the distribution itself, the probability distribution itself, is invariant under the time evolution, but it is not that transitions are not occurring, they are occurring all the time, but keeps the entire distribution unchanged. So is that, does that answer the question? Okay. Okay. I must point out that detailed balance does not have to obtain always, there are special physical reasons in certain systems why it obtains, and then you have a very particularly simple solution to the problem of finding the invariant distribution but that is or equilibrium distribution, but does not have to happen always. But you can, however, in principle ask, is there does yeah.
Isn't it the change in probability and not the probability itself, Pj?
Yeah, this was for the discrete case. So if I want to convert this now to a time equation like delta p over delta t, yeah, then I would subtract from this Pj of n minus 1 and then go to the limit in which the time step becomes 0, and then I end up with the master equation. Okay. So this equation here is for a chain. It just says at time n minus 1 you reach this, at unit intervals I am making transitions, and I have reached this state k at n minus 1, this is the probability, and the next step is to flip to j. So this gives me the probability that having reached the state k at time n minus 1, in the next step I am at state j, and this tells me how much flows out at this stage. I am in the state j at n minus 1, and in the next step I move out here.
So an equilibrium is sufficient if Pj becomes independent of time, right?
Yes, exactly. I have assumed throughout that these things are independent of time, these are constants, some given constants. What would you say is this what sort of chain would you say it is, Markov chain would you say it is, if these were themselves n dependent? Could still be Markov. Markov just means one step memory, but what sort of chain would that be if these were n dependent? This would be like the non-autonomous systems we looked at in the case of dynamical systems. So what would you say, what kind of chain would this be? The statistical properties change with time, and it would therefore be a non-stationary random process. It would still be Markov but non-stationary. And then of course there is no question of a stationary distribution in that case. So I have assumed that this set of numbers is independent of n itself, and the n dependence comes here completely. Yeah. Yes.
That is if
Yes.
you are analyzing a problem that is given to you.
Yes.
Like how do you justify varying the time step so that you
No, yeah, that's a good question. The question is the time step arbitrary or not? Okay. There are problems where if the time step is given to me and it is discrete and the state space is discrete, it is a Markov chain if the Markov conditions are satisfied. Okay. However, there could be other problems which I could start by modeling in terms of discrete time dynamics, but where the dynamics is actually running in continuous time, and then to derive those differential equations I could start by writing down difference equations and then moving to the continuum limit. That is the way you derive differential equations in any case in most physical problems. You start by asking what happens at finite increments and then go to the limit in which delta t goes to 0, and it would lead in general to differential equations.
So whatever stationary process the stationary probability distribution
Yeah.
you are referring to are actually for continuous process.
Yeah.
For these time steps.
No, not at all. I mean, no, not at all. I mean, it has nothing to do with whether it's discrete or continuous or anything like that.
You can't otherwise use the dou p by dou t.
No, I don't have to set that. I would say this is equal to. I mean, if I say this is independent of n.
Sufficiently large.
Yeah, exactly. I take the limit in which n goes to infinity and ask, is there a non-trivial limit? Right? If there is a non-trivial limit, that is my stationary distribution, isn't it? Yeah. So all I have to do is to ask, does this have a finite limit? Does this thing have a limit as n goes to infinity? And the idea is that in most cases, if the chain is ergodic, that limit will be independent of what p of 0 is, as long as everything is connected to everything else. Just like the invariant measure was independent of what the initial distribution was in the case of the dynamical systems we looked at. So in the same spirit.
If it has to be Markov, it has to be always independent of p of 0.
That's a subtle question. Is this true or not is the question. Let me explain this. That's a good point. Let us look at it in continuous time. We saw that for stationary Markov processes everything was decided by two quantities. One of was the probability distribution of the variable itself, the probability density function for continuous variables, and the other one was a conditional density which looked like this. So we have assumed stationarity, we have assumed time is continuous, we have assumed that the state space is also continuous, and these are probability density functions. This one is the one time density function, but that is independent of the origin of time, so there is no t sitting there, and this one was a function of xt, x naught comma t naught, but by stationarity I subtract the t naught out and it is a function of just one time here. Okay. Now the interesting question is limit t tends to infinity p of xt x naught, is this such that it loses memory of its initial condition and becomes equal to p of x or not? This is the question one asks always, and the statement I made was that if the system has a sufficient degree of mixing, then this is true, then this happens. So this is essentially what happens in the case of these Markov processes, the kind of Markov process we are talking about. This is what happens. The fact that it is in continuous time is irrelevant. I mean, I could rewrite this in discrete time, it does not matter.
My question is,
yeah,
shouldn't this be valid for any Markov process?
not necessary, it is not very clear why that should be so.
Because
why should it be so?
Markov processes don't have memory more than one, the previous one.
Yeah,
So
it actually implies, yeah, it implies, this is not necessarily true, it implies that this system, it is not a question of the memory being short, that has been taken care of already in saying that everything, all the joint probabilities are decided by just this 2-time probability. But now if the correlation between the variable, the autocorrelation function of this variable dies slowly enough as t goes to infinity, there is actually no reason why this should happen, why this limit should go to this at all. It is an assumption that is made in general, it is a sort of consistency condition, but to prove it rigorously is another story altogether. So it is not, I do not believe that this is so that as soon as you say the process is Markov that this is true, but I am not 100% sure, I will check this out, but it strikes me that this is independent, this is an independent statement, a further input that has been put into this that has got to be added to the system, but I will check this out. Okay. All right. Let me go back now and talk about the idea of a recurrence, and this is something which we will deal with when we do coarse grained dynamical systems. We looked at a 2-cell dynamics, if you like, for the asymmetric tent map in which you went from the left to the right and back again and so on, but let us do this in a slightly more general setting in higher dimensions in general and see that there is an extremely simple formula for the mean recurrence time which is important to understand. It is called the Poincaré recurrence formula. It is valid for all ergodic systems, does not have to be chaotic or anything like that, and it goes as follows. The derivation is simple, so let me do that, and it goes as follows. So we look at recurrence. Let me call it recurrence time statistics. Okay. We start with a phase space of this kind, arbitrary dimensionality. We will work it out in discrete time in terms of maps, and we could make it continuous later. There are some subtleties involved, but for ease of illustration let us look at discrete time dynamics. And I have a point, an initial point x naught out here, and at time 1 it jumps somewhere else and then somewhere else and somewhere else, and an orbit is formed by this point x naught. Okay. And I ask the following question. I divide up my phase space into cells in this fashion, and I focus on one particular cell. Let me call this cell C. I assume there is an invariant measure, and I assume that the dynamics is ergodic. In other words, any set of initial conditions, that little volume element would visit all of this available phase space given enough time. Okay. I do not assume anything else, just ergodicity, nothing more than that. And now I ask, if I start with the initial point in C, then what is the first time that I come back to C? What is the probability that I come back to C at the nth time step? That is one question. The second question is, what is the mean time in discrete time steps of some time step tau, in discrete multiples of this time step tau, what is the mean time to come back. Then I could ask what is the variance, what is the statistics in general. So I would like to discover what the statistics of recurrences to this cell C look like, that is the target. And I assume that there are invariant measures, there is an invariant measure on this and the measure of this cell C, let me call it mu of C. And let us assume that the whole phase space is its measure, invariant measure is normalized to unity, so I do not have to keep dividing. Pardon me? We computed and we said, well, we said that this is equal to the time step divided by mu. I would like to derive this formula, I would like to derive this from first principles, but in general I would like to derive the statistics itself, not just the mean time, maybe the variance. I would like to find out exactly what it is. So this is the target. Now how do we go about this? Well, it turns out there is a very elegant and a simple formalism to do this, which goes as follows. First let us ask, what do I mean by the probability of a recurrence to this cell? What I mean by it is the joint probability that, and now let me, in keeping with our notation, write earlier times to the right and later times to the left. I want the joint probability that if I start at the cell C at time 0, I leave this cell and I come back at time n. So I want the joint probability that having started here, I am in the complement of this cell, so let me call the rest of it that means the rest of this other than the shaded portion. Okay. So I am in C tilde at time 1 and let me call this time step tau, let me set it equal to 1 for the moment, C tilde 2 and so on till I hit C at time n, C tilde at time n minus 1. So this conditional probability is what I would like to compute. What is that equal to? Well, we know that this conditional probability is a certain joint probability divided by the absolute probability of this thing here. So this is equal to P C n C tilde n minus 1 dot C tilde 1 C 0 divided by P of C 0. But this P of C 0, since I am assuming that the system has an invariant distribution measure and everything is stationary, this P C comma 0 is independent of the time origin, it is independent of this time argument and it is just P of C, and that is nothing but the measure of this cell itself. So this is the same as mu of C. Okay. I use P of C and mu of C interchangeably, they are exactly the same thing. Remember that I have normalized the total volume or the total measure, invariant measure of this phase space to unity. So then I can replace P of C by just mu of C, okay. And it is this quantity I would like to compute. But what is this quantity? Since the variable that I have is this point x naught which moves around here, so let us do the following. Let us write this as a multiple integral over the phase space times what? Now what should I write here? It is d mu, that is the measure of x, d mu, this is rho of x dx if you like, d mu of x over this measure, right, times, what is the first point that I should write down here? I am going to start at time 0 inside the cell, and let me define the so called indicator function chi of x to be equal to plus 1 if x is an element of the cell, equal to 0 if x is an element of C tilde. It is like a theta function. So it is equal to 1 if the point is inside and 0 if it is outside, that is it. Since I am going to start there, so this is chi of x definitely. And how does this x evolve? We have already assumed that this x evolves xn is equal to some f. Let me not use this cumbersome notation, it is some operator t acting on xn minus 1. This is the map function if you like, but I have written it here as some operator which acts on xn minus 1 and produces x sub n, just for ease of notation. This is the time development operator which takes me from time n minus 1 to time n. Okay. So what happens next? At time 1 it should be outside, therefore you should multiply this by 1 minus the indicator function of t on x, because at time 1 this guy should be outside, and the same thing should happen for time 2 and 3 up to n minus 1. So let me write a t power k which says this is the same map iterated k fold on x, a product from k equal to 1 up to n minus 1, and then so you start here, you jump out and you stay out and come back at time step n. So the last factor is chi at time n, so it is t n x. So formally this is this probability, the whole thing normalized by 1 over mu of c. So although the notation looks elaborate, the reason for it is it is in complete generality. So very complicated time evolution is taken care of here by writing this abstract operator t. If this is a set of very complicated nonlinear map, it is still taken care of by writing this, and this tk stands for the kth iterate of this map, just as t to the n is the nth iterate of this map, and you have to do this integral in principle, and that gives you this conditional probability, which is the probability of a recurrence to the cell at time n. So this is the probability with respect to which I start taking averages, but first I have to compute this number in some simple fashion. Now let me introduce the following auxiliary quantity. Let me define Wn tilde to be equal to the probability, so for that I just write P, probability, that if I start in the complement of this cell at time 0, I remain there till time n minus 1. Okay. So this stands for C complement 0, it is a joint probability here for starting there, remaining there, all these do exactly the same thing, and the last one this is the definition P of being in this cell C tilde at time n n minus 1, okay, n greater than equal to 1. So I define the measure of those events where I start with the representative point in the complement of this cell and I do not leave this at all, I do not leave the complement, I do not enter the cell C, but at time n minus 1 I am still in the complement. Pardon me? All of them are C tilde, every one of them is C tilde. Yeah. So I do not enter the cell C at all. So here is C and the rest is C tilde. So I start somewhere here and the orbit goes on here but never enters this. The measure of that set of points, let me call that Wn tilde. It is clear that W1 tilde is equal to, if I said n equal to 0, n equal to 1 in this is just the invariant measure of C tilde. So this is mu of C tilde because it is just P of C tilde 0, the origin of time does not matter, so it is just mu of C tilde, and therefore this implies a very useful relation which is mu of C equal to 1 minus W1 tilde. Because remember the total measure is 1, so mu of C plus mu of C tilde is equal to 1 by definition, and therefore mu of C is 1 minus W1 tilde. Let us also further define, it will become useful, W0 tilde to be identically equal to 1 itself. We will see why that is necessary and useful. Okay. What can we say about this sequence Wn tilde? This is a sequence of numbers now, starting with 1, W1 tilde is some number less than 1 between 0 and 1 and so on. What can we say about this set of numbers? Is it an increasing sequence or a decreasing sequence as n increases? It should decrease because this is the probability that the system does not enter C at all. So it is a sequence which is bounded from below because these have got to be non-negative numbers being probabilities. So the sequence is bounded by 0 from below, starts at 1 and is a non-increasing sequence bounded from below. Therefore there is a theorem in analysis which says such a sequence has a limit point. In other words, just the statement that this sequence Wn is a non-increasing sequence bounded from below. By 0 because it is clear that this set of numbers can't become negative, implies limit Wn limit n tends to infinity Wn tilde exists. That is a rigorous theorem in analysis. There is no reason why this limit should exist, it could just oscillate, but this is guaranteed that such a limit point, such a sequence has a limit. Okay. Now what does ergodicity have to say about this sequence? What would you say is implied by ergodicity for this limit? We know that given enough time any set of initial conditions has to visit the entire phase space including C. Therefore it is quite clear that as n increases and n tends to infinity, what is the limit of Wn tilde? Should be 0 by ergodicity. So that is the assumption, that is the rigorous assumption which says by ergodicity, and let me write that here, this is where the input goes in, is strictly 0, and this limit exists and is in fact 0. Okay. Now let us try and simplify this a little bit. So what is the trick one would use? Well, if you had only these factors and nothing more, just a set of these factors, then you can easily see that it is related to this sequence because this is precisely the probability, joint probability, that you start with C tilde and you remain in C tilde if you had this thing here, but unfortunately you can't do that because you have this factor and you have this factor. What would you suggest? We somehow have to convert them to these factors, so what would you suggest? Add and subtract 1, right? You would add and subtract 1, this is all you would do. So if you did that, then the following happens. So let us do that, and then a remarkable formula emerges. So this P of C n, C tilde n minus 1, C tilde 1, C 0. So for the moment let me just look at the numerator. So this 2 is unconditional, which is this multiple integral could be written as equal to integral d mu x times, instead of chi of x, let me call this 1 minus chi of x and then subtract the 1. Should be careful about minus signs though. So let's do that slowly. So let me write chi of x, chi of Tn x, let me write this quantity and subtract the rest of it out. So this minus, well, the first term that I have to subtract out is this 1 clearly, and then what else do I have to subtract? I hope I am not what else do I have to subtract? Plus chi of x plus chi of t to the power n x, right, minus 1, I write it in this fashion. Okay. Now if I plug this in here, if I put that in here, then what would this integral become? It would say you are going to start at z, so it would correspond to starting in the cell C tilde at time 0 and then continuing all the way up to time n here. So what would that become? It would be W tilde of n plus 1, because we define W tilde of n as staying in this complement from 0 up to n minus 1. So you would immediately get a W tilde of n plus 1, right, and then you have this term and this term, right. So let us write this once again by adding and subtracting, right. I write this as equal to, so this portion, let me rewrite this as minus 1 minus chi of x, right, in this fashion. So that takes care of this portion, and then I am left with this, and this term, let me write it as this term as equal to minus 1 minus chi of T n x, this fashion. And what have I done now? I have subtracted this, so I write it as plus 1, right. So I put them all together and what do I get? I end up with this probability is equal to, we already saw that you had a Wn plus 1 tilde, and this term here corresponded to just the product pi from k equal to 1 to n minus 1 there, right. So that would give me W tilde of n minus 1 plus W tilde of n minus 1, that takes care of this term and it takes care of the original term, this term, this product, and then I have minus this minus that. Now what is this term? So this says you are going to sum with this product. Now what does that say, what does that give you? It gives you W tilde of n with a minus sign. What does this give you?
Tilde of n plus 1 minus the origin.
What does that give you? That is where you need a little bit of subtlety, because this term here is really saying it is integral d mu x, let us write it out, product from k equal to 1 to n minus 1, 1 minus chi of t n x, tk x, and then it is multiplied by 1 minus chi of t n x, it is this term. Agreed? So I could make this n and get rid of this, but what is that equal to? What is that equal to? Unfortunately I can't write it as a W immediately because the integration is over x, but the characteristic functions here are over Tx and k runs from 1 upwards, unfortunately.
1 minus.
1 minus.
What use is that going to be? It is inside the integral, it is inside the integral, unfortunately. So what can I do about this? You are integrating over x, which is the time 0 if you like, but then everything else is happening, all the integrand involves whatever happens at time 1, 2, 3 etc. So this is giving you the probability, some kind of probability it is trying to give you, but it is over Tx, t squared x and so on. But you see this is an invariant measure, that is the whole point of invariant measure, that if you apply the t operator to x, the invariant measure does not change at all. So this is true, that is the meaning of invariant measure. So it does not change at all, which implies I can change variables from x to tx and nothing happens, and once I do that then this becomes Wn immediately. So that gives you another factor of Wn, which is twice this divided by mu of c to get the actual recurrence probability. So we collect all these results and let us write our final result, which is that this conditional probability that we are interested in, this thing here is now been rigorously proven to be equal to W n minus 1 minus twice W n plus W n plus 1 tilde divided by mu of c, but mu of c was 1 minus mu of c tilde, but c tilde was W1 tilde, but we defined this to be W0. So So that gives you the actual recurrence time probability. This is the probability after time interval n. You are guaranteed, we have to check normalization, but you are actually guaranteed that this is a positive number, because this is a decreasing sequence tending to 0 in the limit, and therefore this is like the second derivative of this object, and this, you can see that it is actually saying that this sequence, if you plot as a continuous function, is concave upwards, because it has got a lower limit which is finite. So this quantity is non-negative and is in fact the exact probability distribution. But you can now ask what is the mean time to recurrence here. Therefore if I call that mean time to recurrence to the cell C, T sub C, this is equal to, first of all I need to show that this is normalized. You have to make sure that this guy is normalized. So let us check that out first. What is, and let us give it some number, some name. So let me call this guy R for recurrence, C of n, let us call it RC of n. We have to make sure that summation RC of n over all allowed values of n should be 1, otherwise there is no guarantee that recurrence is a certain event. We know it is ergodic and it better be equal to 1, but we got to make sure of this. So what is this equal to? What is the least value of n for which this is valid? From 1? 1? Alright. So what do you get? So this is a common factor times, if you call it 1, then this is W0 tilde minus 2 W1 tilde plus 2 tilde plus W1 tilde minus 2 W2 tilde plus W3 tilde plus W2 tilde minus 2 W3 tilde plus etc. What happens now? So it is quite evident that W2 tilde for example will appear twice and get cancelled, so will W3, W4 etc., and you are left with just finally, so everything gets cancelled except W0 tilde minus W1 tilde plus twice, plus single times W1 tilde. So this whole thing collapses to just this. Okay. That is equal to 1. So it is evident that if you, this thing is normalized. It is a normalized probability distribution. Now we can find the average. Now what is the average distribution? What is the average recurrence time? So since we are using n at discrete time, n, see this is the mean for cell C. What does this give you? This is equal to a summation n equal to 1 to infinity n times r n RC of n. Now what is this equal to? So again this is simple to see, it is 1 over W0 tilde minus W1 tilde multiplied by 1 times this, so W0 tilde minus 2 W1 tilde plus W2 tilde plus twice when n equal to 2, so it is twice W1 tilde minus 4 times W2 tilde plus twice W3 tilde plus now thrice the next one, so thrice W2 tilde minus 6 W3 tilde plus thrice W4 tilde plus dot 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 etc. So this obligingly cancels out, and what are we left with? So this guy cancels out, so twice this plus 4 times that minus 6 cancels out, and so on, everything cancels out, and you are left with this is equal to W naught tilde over W naught tilde minus W1 tilde, but W naught tilde is 1 by definition, and this guy is 1 minus W1 tilde, which is the measure of the complement, and therefore it is 1 over mu c. So this whole thing finally is equal to 1 over mu c. In time steps of 1, had we used a time step tau, it would be tau over mu c. Okay. This is the Poincaré recurrence theorem. So it proves rigorously that when you have coarse grained dynamics of this kind, if the system is ergodic and has an invariant measure, then you are guaranteed that the mean time of recurrence to any cell is inversely proportional, is just the reciprocal of the measure of that invariant measure of that cell. A very useful piece of information and a very general statement. We went through a little bit of formalism, but it is a very general statement. The assumptions were minimal and completely rigorous. We just assumed ergodicity and the existence of an invariant measure, and this statement follows at once. If you have time steps which then go to 0 continuously, that becomes a little more subtle, because it is not very clear if this formula can be just translated directly, because if I put a tau here instead of a 1 and let tau go to 0, then formally any finite measured cell will have a 0 recurrence time, which is absurd, and that is because of a flaw in the argument which does not take this possibility into account. We counted as a recurrence something where the system stays in the cell itself, because we started at n equal to 1. So really you should start by saying it goes out and comes back, and then taking the continuous time limit is a little trickier. You have to subtract the measure of all those points, all those events where the system starts at time 0 in this cell and remains there at time 1. Now that is a fake recurrence with a recurrence time of 1. So you should subtract that, and if you improve the formula, for which there exists such a formula, then you get an improved formula for this which changes this slightly. But in general, apart from that technicality, this is a very general result which is useful in many cases. So it gives you a quick order of magnitude estimate of how long it takes to recur here. Now this is used in principle even in statistical mechanics in large systems. It turns out that this is the time for coming back, the Poincaré recurrence time, the mean time, and when you have a very large system, then this thing here can be shown, the time can be shown to grow like the exponential, some exponential of the number of degrees of freedom, which is why the macroscopic world appears irreversible to us, because even if the statistical properties did not change and everything went on as before without aging, even then the time for the system to recur would become exponentially large in the number of degrees of freedom, and if you have 10 to the 23 degrees of freedom, then this is more than astronomically large. E to the 10 to the 23 is so large that it does not matter whether I measure units in time in units of seconds or microseconds or ages of the universe, it does not matter at all. It is exactly the same impossibly large number. So that is the reason why macroscopically things appear to be irreversible, even though in principle if you did not have any dissipation, you had dynamical systems which, for even if you said that the system was conservative and did not have any irreversibility built into it, the recurrence times would become impossibly large, unrealistically large. That is the reason you do not see it in practice. Okay, I do not want to get into the details of macroscopic irreversibility here, it is a subject by itself, but this result is used in deducing these orders of magnitude. Okay, so let me stop here and we will continue next time, a slightly different topic, we will go back.